Hello and welcome to this video on centripetal and centrifugal forces. If you've ever wondered how it is that a centrifuge works or why a bucket of water swung around you will not spill, then this video has the answers you seek, although we cannot speak to the speed of an unladen African swallow. Centripetal or centripetal and centrifugal forces are fundamentally two sides of the same coin. They are both intrinsically linked but also slightly different. In this case, both of the forces we talk about when something goes in a circle. First, the force that we're talking about is going to involve an object going in a circular motion, and this is centripetal force. This is always directed towards the radius of the circular path. In other words, anything going in a circle will experience centripetal force, or in fact anything making a turn. The force that keeps an object moving with uniform speed along the circular path is going to be important, although it doesn't necessarily need to be uniform speed. If speed increases, you get an increase in that force. By contrast, centrifugal force is something of a misnomer. Centrifugal force is more how we perceive what's happening, or perhaps it would be more accurate to say, it's the sensation an object feels when it's moving in that circular path. It is a sensation that you're being pushed away from the center of the circle. Those two descriptions are perhaps an awkward description that's hard to understand. If you think of it this way, centripetal force is the general nature of an object to want to move towards the center of a curvature, whereas centrifugal force is the result of that happening. Just remember, in any situation, the only force that is actually working is centripetal force. Centrifugal force isn't actually happening. What you find is that whatever is on the outside of the circle is more what's being displaced. To simplify matters, you can say that centrifugal force is the name for movement away from the center of a circle. Centripetal force is the movement towards the center of a circle, although this is an oversimplification and doesn't quite capture the whole story. It is a short and simple summary of what we've just said to begin with. In practice, things are both simpler and more complex. They are simpler in that you can clearly see the difference. They are more complex in that you need to consider more variables. The easiest thing to look at is mass. Things with more mass will move to the outside of the circle. That is, the centripetal force is more affecting them. They displace the less mass objects, and these get moved towards the center. Things in, say, a test tube get sorted by mass, and so the heaviest things are on the outside and the lightest things are on the inside. This is why a centrifuge separates out the contents of a centrifuge tube, like blood. By contrast, those things that are lighter will move away from the center, as the centripetal force is less pronounced on them. That allows for separation by mass. This is something you can see when gold panning. That heavier gold flows away from the pan center, while lighter sand and rocks stay towards the center. All of this demonstrates Newton's laws of motion nicely, and specifically Newton's first law, which states that a body at rest will remain at rest and a body in motion will remain in motion, unless it is acted upon by an external force. In other words, once you start to move something, it will keep moving unless a force works against that. In this case, the circular motion is the force trying to stop a stationary body. As you spin the body in a circle faster, it needs more force. The things that are acting against this would be, say, gravity and resistance, specifically resistance in the form of friction. Other than that, you can pretty much calculate this fairly reliably. You take the radius of a circle, and you need to then figure out the mass of the thing you're trying to spin, along with the velocity. This then gets you r equals mass over velocity squared over f, f being the centripetal force. The force can be calculated by rearranging the equation to F equals the mass times velocity squared over radius. If we're talking solely about a rotating system, the centripetal force will pull the mass inward, and this will hopefully follow a curved path. If it doesn't, things are going to go very badly very quickly. So long as it follows that curved path, the mass appears to push outwards, and that's the effect of inertia. Inertia being something staying stationary unless a force is applied to it. and that force in this case is centripetal force. This is where we need to mention a slight caveat. Centrifugal force is generally called an apparent force. That's because although you can see an effect, the actual force itself doesn't exist, it's solely a consequence of centripetal force. Under normal circumstances of gravity, the thermal motion causes continuous mixing with blood, and so this is why when you have a blood sample, it's simply a tube of red liquid. It's a combination of plasma, proteins, cells, and more. By taking a typical laboratory centrifuge, you can get it to accelerate to ridiculous speeds. These speeds cause something to the effect of 600 to 2,000 times the normal effect of gravity on the tube you've put in there. This leads to the red blood cells, which are the heaviest parts of the blood, being moved to the bottom, or the most outside part of the tube. Then you have the slightly more heavy elements above that, and then progressively more light elements until you finally have what is just a layer of plasma on top. This layering is a result of the inertia in the red blood cells being most pronounced, with the plasma being the least dense and therefore least heaviest substance, having the least consequence or least resistance from its inertia. To show how this works yourself, you can try swinging a bucket of water overhead on a string, or more accurately rope. Remember to keep it in a circle at a right angle to your body. The water will not spill out. That's because the water is being pulled towards the bottom of the bucket, which should face away from you. That means the water is always being pulled away from the opening. The moment you slow down to a point where the centripetal force no longer outweighs either gravity, or is no longer able to pull on the water enough, the bucket will either fall, or conversely the water will fall out. A ball also works in the same way, although far less fun. This is in many respects very similar to how a hammer toss in Olympic athletics works. They spin very fast in a circle. This creates a force pulling against them and the hammer, because of the hammer's weight. The hammer does not want to move, that is inertia. By spinning the way they are, they're putting force into it, and once they reach what they view as a terminal velocity, the hammer is released and flies away. That is because you are no longer trying to stop the body or hammer in this case from being stationary, as you've released it. That allows it to convert the energy from potential to kinetic energy as it flies away, using that energy to become stationary once more. An even older example would be the trebuchet. As its weight is dropped, it raises the basket or sling. That is spun up to 360 degrees until the shot is released. It is at the end when the circular motion, and as a result the centripetal force is removed, that the power goes from centripetal to linear, or more accurately kinetic, force and sends a 100 or more kilogram chunk of rock flying. Once the rock gets to the target, the remaining energy is dissipated either as heat or transferred to the target, and this is what causes the damage. Overall, centripetal force and centrifugal forces are the same thing. Well, strictly speaking, centripetal force is real while centrifugal force is perception of force, but most people would struggle to need that distinction. What is important here is to note that centripetal force is pulling things away from the center of a circle, while centrifugal forces are quasi-pulling them towards the center of a circle, or at least that's how we perceive it. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you have below.